Hi, my name is Dai. In this summer project, I work with Sam, Marty, and Yusuke on the project that generate time series energy data with GAN. So why do we need synthetic data? Australia, alongside with many other countries, have targeted to reach net zero by 2050, and data sharing in the energy sectors is important to achieve that goal. However, data sharing is limited by the concerns about privacy and legal issues. So one emerging solution right now is that instead of sharing real data, we're going to share synthetic data that has the similar characteristic and patterns to the real data. So our project goal right now is that we would like to generate time series energy data using a generative adversarial network, also called as GAN. The synthetic time series should mimic the typical real data patterns while avoiding the replications of sensitive outliers or unusual patterns from the original data. And also we would like to implement some privacy protections filter within the generative model to prevent potential sensitive data leakage. This is our experimental flow. After combining and processing data, we like to whether we have an option to use or not use the differential privacy. And if we do, we gonna use differentially private stochastic gradient descent algorithm alongside with a GAN model. In here, we're gonna use doppelganger, which is a type of GAN to generate synthetic data. And then after that, we're gonna apply similarity filters to get the final synthetic data. So in here, I like to talk about doppelganger, which is a type GAN that we used. So it was first introduced in 2020 with the goal to address some common issues in GAN, which are the inability to capture the long-term effects as well as the mode collapse issues. So the mode collapse issues occur when the synthetic samples are similar or identical to each other. Doppelganger addresses those issues by employing LSTM in the generator to sequence data and output multiple time points to enhance the temporal correlations. And it also uses the Wasserstein loss function to mitigate the vanishing gradients and address mode collapse issues. We use differential privacy to train the GAN models. And what is that it makes it possible to share information about individuals while maintaining the privacy of individuals. DB allows the training models not depend too much on individuals' user data, and therefore it can help mitigate the risk of exposing sensitive training data in machine learning. So in here, we in particular use differentially private stochastic gradient descent that is provided by TensorFlow privacy library. Basically, what it does is that it gonna controls the noise being added to the gradients. And we integrated the DBSGD from the original doppelganger repository into the codebase of the Y-data synthetic package. So I like to talk about similarity filters here. So what it does is that it's a synthetic series that gonna be filtered to remove the similar series compared to the original series. Using either RMSE or cosine similarity matrix. So the score gonna be calculated for each pair of the original and synthetic time series, and we can use the threshold to remove the similar generated series. So some of our conclusion is that the experiment can effectively capture the short-term patterns observed in the real dataset, but still struggles with the long-term patterns, and the models requires intensive training time. Some future work that we'd like to do is that we'd like to explore solutions to generate more dynamic time series, as well as some solutions to capture the long-term patterns in generating time series. And yep, I'd like to thank Sam, Marty, and everyone from Pawsey for this amazing opportunity. It's a great honor to be able to work with amazing people, and I have learned a lot from this experience.